As we begin our third lesson on the chapter on the atoms and elements, let's first briefly review what we went over in the last lesson. We talked about Dmitri Mendeleev and how he is the architect of the periodic table, and he laid out the elements according to their mass in rows and columns, and in doing so he aligned them so that those elements that had similar properties were in the same column, or what we call a group. And in this periodic table, it's organized so that the left-hand side is where we find metals, and they all have somewhat similar properties. And then on the right-hand side, especially the upper right-hand side, we have the nonmetals, which have distinctly different chemical properties, and including the ones on the far right column, which are the inert gases or the noble gases. And then in between we have elements called metalloids. Now in this lesson we're going to further talk about the atom at the subatomic level, that is the actual components that make up an atom. As we said last time, each of the elements is given a name. If you exist, you need a name. We have hydrogen and helium and lithium and beryllium and carbon, etc. And these elements differ in terms of the number of subatomic components. And we'll talk about those in a second. But if you remember looking at the periodic table, you saw something that looked like this. For example, this would be what would be seen in the little box for carbon. It would have the symbol for carbon, perhaps the name, that helps. But it would have the number of a number like 6, which is the number of what we will call protons, which we'll explain in a second, and above it. And then below it, there would be another number, which is actually the sum of the number of protons plus another subatomic component called a neutron. Okay, so if you look at the table in this slide, it lists the 3 important elementary subatomic particles that we find in an atom. We have a proton, a neutron, and an electron. The second column gives the mass of each of these. A proton is assigned a relative mass of approximately 1 AMUs. An AMU is something called an atomic mass unit. It's just a unit that describes the mass of a particle this size. We'll talk more about that in a second. A neutron has about the same mass as a proton, approximately 1 AMU. But notice that an electron is much smaller. It's approximately 1/2000th of the mass of a proton or a neutron. Now, these particles also may have charge. A proton is assigned an elementary charge of +1. An electron is equal and opposite, -1. And a neutron, as the name implies, has 0 charge. Now, what are these relative charges and masses, an AMU unit? Why don't we give the mass of a proton in terms of something we could weigh, like grams? Well, we can, but the number would be very, very, very small. And as you see, 1 AMU unit corresponds to a mass of 1.66 times 10 to the minus 24th grams, an extremely small number. So it would take a lot of protons in order for us to actually be able to weigh those protons, because we don't have balances that can weigh a mass that small. That's why we oftentimes talk about relative units. An elementary charge also has a value in terms of coulombs, which is a unit of charge. And again, the actual charge on a proton or electron is a very, very small, 1.60 times 10 to the minus 19th coulombs. Now, to give you some idea of the magnitude of these small numbers, let's consider an M&M. Now, M&Ms are great because the mass of an M&M is about 1 gram, almost exactly 1 gram. Now I'm talking about the plain M&Ms, not the peanut. The peanut M&Ms are almost 2 grams. And also, as a brief digression, did you ever notice that a bag of M&Ms has only M? There are no M's in a bag of M&M. It's just one of these things that I find a little odd. So if a M has a mass of 1 gram exactly, let's just say that it's exactly 1 gram. Notice also in this slide I have a small dot. Now you may not even be able to see this dot, it's so small. But let's just say that that is one of these elementary particles like a proton or a neutron, and that it is equal to 1 AMU unit, 1.66 times 10 to the minus 24th grams. So the question is, how many of these dots, AMU type of dots, do we need to build up 1 M&M? Well, if you think about it, if you had 100 of these dots, the mass would be 1.66 times 10 to the minus 22nd. If you had 1,000, it would be 1.66 times 10 to the minus 21st grams. So still very, very small numbers. So how do you determine how many of these dots you need to build up 1 gram's worth of an M&M? That's the question. How many proton dots would be needed to make 1 M&M? Well, to do the math, quite simply, you say that you need X. X is the number of these proton dots that you need. X times the mass of an individual one, 1.66 times 10 to the minus 24th, would then be equal to 1 gram. So you solve for X, and X turns out to be a very large number, as you might guess. You need a very large number of these dots, these elementary particle dots, to build up an M&M. You need 6.02 times 10 to the 23rd. Now this is an important number to chemists. It is something we call Avogadro's number. Avogadro must be a person behind this name, or this number. Avogadro was an Italian scientist and lawyer. His full name was Lorenzo Romano Amadeo Carlo Avogadro di Corregna e di Cerreto. And he came up with this concept of this number. This is just a common, oh hey, I just met, it's crazy, can you give me a call? What number to call? 602 10/23. Okay, now this number is also called a mole. It's sort of like a chemist's dozen. Just as we cannot weigh such small amounts of material as one of the dots on my previous slide, we have to scale up. And we scale things up into the mole range, that is the number of these particles in the range of a mole, so that we could actually weigh them, and so that they're the size of like an M&M. This is just a little picture of a mole. Why it's called a mole is probably because it's the root of the word molecule, not because of the animals. And to give you some reference for the size that we're talking about, Avogadro's number is 6.02 times 10 to the 23rd, if I write it all out, and then compare that to the U.S. national debt as of the year 2014. So you can see that Avogadro's number is quite a large number, and it's just much larger than even the value of our debt. Now we're going to take a break again and have you answer a few questions before we move along to the next chapter.